look at the big idea first. Now, the big idea usually comes from what the state's content statements are. We'll see how we can tie in what we're doing to what is required by us. Then we have an essential question, and that leads into our challenge. And we kind of all know what our challenge is, but I'm going to go over a little bit more of the specifics today. And then your group is going to come up with some guiding questions that will help you be successful for the challenge. Okay? So, first of all, the big idea. We're finishing up one big idea, and we're starting into another. That's why this challenge fits perfectly in between them. Okay? So, the big idea, the Earth science big idea that we're just finishing up is that thermal energy transfers in the ocean and the atmosphere. Thermal energy transfers in the ocean and the atmosphere contribute to the formation of currents, which influence global climate patterns. We just studied that. We looked at the NOAA drifter buoy data. We looked at how they use those buoys to determine temperature. Remember, we tried to determine if the water is warmer in the northern hemisphere or the southern hemisphere, and what did we find? Ooh, it's okay. What'd you say? Too close. Too close to tell. The water's about the same. But that's one thing that they look at. They look at temperature data. So we're going to use that now and make a buoy ourselves to look at temperature in a local water source, which is Mill Creek. That's the one we're finishing up. Now, this now leads into the life science. For the rest of the year, we're going to be looking at life science. And the new big idea, the new concept statement is, in any particular biome, the number, growth, and survival of organisms and populations depends on biotic and abiotic factors. Okay, so biotic means living, things that are living. BIO, bio always means life, or living. Abiotic are non-living factors. So what's one big non-living factor that affects an ecosystem? What we're looking at. Temperature. Oh, did you say chemicals? Yeah. Chemicals and temperature. The chemicals in the water, when we do the chemical test, plus the temperature, and that's what we're creating our buoys for. Now, I put this picture here. This is, you know, I've been doing Mill Creek since way before you guys were born. This is a picture of how we used to do the temperature reading. You had to get these big boots on, you had your goggles on and gloves, you just had a thermometer, and you stuck it and held it in the water. So what we're going to try to do is make it easier. We're going to try to create a buoy that we can send into Mill Creek where it will take the temperature for us instead of us having to stand there. Okay, so this is going to be the engineering activity. So this is our big idea. The essential question for this unit is, how can the study of global drifter buoy data help us test the conditions in our backyard? And you know, that one we're doing there is, we're understanding the idea of buoys, we're understanding the idea of testing temperatures and why it's important. So here's our challenge. Our challenge is to engineer and release a buoy into a local water source to collect temperature data to help determine the health of the stream. We're looking at, that means it's to help determine, because we're looking at chemical factors, we're looking at biological factors, remember we're going to look at microinvertebrates. So this is one part of that. Okay, now in your folder you have this. Will someone get that out of your folder, please? This is the challenge, and I'm going to go a little bit into more specifics. This is from NOAA. Remember NOAA, the National Oceanic Association that did the drifter buoys? This is their idea for how to make a buoy yourself. So here's an idea, and they've got some pictures here of the materials you're going to use, and they've kind of made some buoys, but I don't want you guys to copy all those. So it says materials you'll need: an assortment of PVC pipe, assortment of PVC pipe connectors, wire ties, frisbees, and golf balls. Your first challenge is going to be to make a buoy to see whose buoy can hold the most golf balls. Okay? So here's my buoy that I made. Now, okay, so first of all, this necessarily isn't a very good buoy. I'm just telling you now. So I don't want you to copy this. But you want to make something that will float in water and hold the most golf balls. And here's, I've got a bunch of golf balls. So what we're going to do is you're going to design it first, and you can informally test it here. Because if it's going to tip over, if it's not going to hold enough golf balls, whatever, you can informally test it and I'll have the water in it. When we do our formal test, we'll do it in that Barcelona football pool. Because we're going to have to create ways and do everything else. Okay?
Are we doing that
today? No, we're just starting today. And then it says, excuse me, it says procedures or process you'll follow. Develop a plan and a hypothesis. Building a buoy with a wide base and tower with frisbee placed on top will result in a buoy that floats and carries the most golf balls without sinking. Build your buoy, use the assortment of PVC pipe and connectors, test your buoy, and then if the last thing says, if you observe that your buoy doesn't float and the golf balls roll out, think about why it didn't work and then redesign it. Okay, so that's always a big part of the engineering design process, redesigning. Okay, so that's what we're doing here. In your folder, I think, Wilmer already says that mine won't hold any. Don't say why, but I just want you to think about it. So think about your design. In your folder, you also have paper, it says what it will have to do. You'll get 10 points if your buoy doesn't tip over, 10 points if the golf balls stayed in, 10 points for if it doesn't tip off when you put waves on it. And then we've also got, what we're going to use at Mill Creek is this temperature sensor. Now when we actually go, we'll test this here, but then we'll also take this to Mill Creek. This is a temperature sensor. It's a two-way temperature sensor. So when we actually go to Mill Creek, this is what you'll put on your Frisbee instead of the golf balls. We really don't need golf balls for Mill Creek. That's just kind of to test it, see how much payload it can hold. Okay, so we'll put the temperature sensor in here. The wire will go down to the water to test the water temperature, and then this part tests the air temperature. So on your Mill Creek data sheet, you have 2 places for temperature. Okay, so we're going to also test to make sure that this will hold the temperature sensor without tipping.
Pardon the interruption.
Which I hope it doesn't.
At this time, we're all 8th grade students.
Okay.
Please take everything to your locker and then report to the middle school auditorium.
We got that.
All 8th grade students.
I want to tell you exactly what your group is going to get. Next Tuesday, when we start building this, I will give you some sort of container. I'm not sure what, but this is just what I found. This is the materials you're going to have. You're going to have 4, and I want you to know what these are called. These are called elbows. And these are 1.5-inch elbows, and these are, you also have half-inch. This is 1.5-inch pipe, and this is half-inch pipe. What do you think the difference is? Why is this 1.5 and this is half an inch, Charlene?
That's for the bottom piece.
Well, right, but why is this called 1.5 and this called half-inch?
Because that one is little.
Right.
Diameter.
Good. Because the diameter of this, so when I say 1.5-inch, this is the 1.5-inch PVC pipe. This is a half-inch. They're both 6 inches. You're going to have elbows to connect the 1.5-inch pipe, and then you're going to have 3-way connectors to connect the half-inch. You'll have a Frisbee, and this is where you put your golf balls and the temperature sensors. You'll have some cable wire ties, 14-inch long. Question? Kenny? No. Jeffrey? If yours can hold, supposedly the world record is like, I'll have to look it up. It says on that thing 12 or 13. If you can hold 15 or more, I'll give you some extra points, okay? World record? So,
15 balls over there, you got it. What if we get
Okay.
16?
Then you get extra credit. You also are going to get 8 of these 3-way connectors. Okay, so you need to have 3-way connectors so that you can make it, excuse me, you have to make it 3-way so you can have it 3-dimensional instead of just a square. You want it to be a cube. So you'll get 8 of these also. Okay? All right, 8. Yeah.
Do you mean the cost?
Yeah. Zip ties 14 inches. So I connected all this with these and then I cut off the excess because they were sticking way out. Okay. So now, and when we go back to the.
No, you said I can do it. You said I can do it. You said I can do it.
I know, but you're kind of trapped. Let me go back there and push, or just check it. Just push it down so you can see the bottom question.
Hi.
Okay, so this is what your group needs to do right now. Okay? You and your group need to come up with 5 guiding questions that you need to understand to help meet this challenge. Okay? 5 guiding questions. So it can be different aspects of the challenge that you need to understand. What makes something float or tip over? Where, think about where you're going to put the Frisbee and why would that make a difference. Think about how you're going to place the Frisbee or this to hold the most golf balls or to keep the temperature sensor dry when we go to Mill Creek. Okay? So think about all the different things that you need to understand and consider when building this. Like someone's already said that mine won't hold any golf balls. What do you know that leads you to, don't say it out loud, what do you know that leads you to believe that mine won't hold any golf balls? Don't say it. Think about that. That will help you determine what kind of questions you're going to ask.
So do you want to write that?
So you and your group right now need to come up with, you and your group, huh? One Frisbee. You and your group need to come up with 5 guiding questions that you need to understand to help you be successful. Now, don't just consider that we're going to test it in the classroom, too. What else do you need to know to be successful in Mill Creek when we actually go there with the temperature sensors and your buoys? Because you are really testing these, okay? So, right now, if one of your questions cannot be what materials are we using. You guys always come up with that. In the past 2 times, it seems like our guiding questions are usually what materials are we using, how big they are, how many. You know the materials. I want you to think about the big ideas. What do you need to understand to make this successful in the classroom and when we go to Mill Creek?